And welcome to the webinar. My name is Philip Stoughton. I'm editor of EMS Now, and we've got an interesting webinar today, which starts with a simple mathematical formula: AXI plus AOI equals AXOI. We'll let David explain what all that means. Before I introduce you to David and before we start, a couple of housekeeping things. We've got your details through your registration, so we'll be able to send all of you the presentation afterwards. We'll also be making an audio recording, which will be available on demand in a couple of days, and we'll also be sending further information out. So you don't need to take notes, you don't need to record the webinar, because we'll be doing that for you, and that will be available online and on demand for you to share with other people. The webinar today is on the topic of AXI and AOI, X-ray inspection and AOI inspection. Inspection is certainly a hot topic in the industry at the moment. Lots of people talking about it and considering whether there are limits to particular types of inspection and how we can use hybrid or combined inspection to come up with the right solution. Hopefully today's webinar will provide some insight into that. As we go through the webinar, I'm sure you'll come up with some questions that you want to ask. Very simply, just click the question tab on your screen. You'll either have a questions piece in your panel if you're on a laptop, or you'll have a question mark icon if you're on a tablet. Just click on that, type in the question anytime during the webinar, and at the end of the webinar session, I will ask David those questions and we'll run through those. Any questions that are left after our hour's up, we'll refer to David and his team via email. We will have another member of the Goepel team joining us for the question and answer session, so hopefully we'll be able to give you detailed answers to whatever you have to ask. But as I say, feel free to put those in whenever you're ready. Let me introduce to you David Whetstone, who is with Goepel, Business Development Manager for the USA, and he is going to give us a presentation, which I think will last around about 30 or 40 minutes, and then we'll go into the Q&A session at the end of that. David, I'll hand over to you.
Thanks, Phil, very much, and thanks to everyone for attending today's webinar. That was actually a really good introduction, Phil. The subject that we're going to talk about today, as Phil mentioned, is largely surrounding or involving AXI, in particular 3D AXI, 3D X-ray inspection, but we also want to touch on the point of combining 3D X-ray with optical inspection. Each of these platforms have their own strengths, and with that, when you combine them, you really get the best of both worlds, and that's what we're really presenting here today relative to the claim of 100% inspection. Of course, there's usually not any such thing as 100% inspection, but the combination of two platforms like this get us, I think, as close as possible, as you'll see. I'm going to talk about the system itself, our particular system. I'm going to talk about X-ray in general, and so I'm going to cover quite a bit of territory here. As Phil mentioned, I've got an applications engineer on board today, so if there are some detailed questions that you would like to dig into later, we can do that. And also, we always invite you, of course, to contact us after the webinar, and we are always happy to provide more detail or even demos as necessary. And with that, I'll go ahead and get started. The content of today's webinar, as I mentioned, I'm going to talk about just the basics of how X-ray works. I'm going to show some examples of what X-ray looks like, how it reveals particular faults, and I'm also going to compare those to AOI. I'm going to show some examples of a production line for APC conformal inspection that involves X-ray, and then talk a little bit also of how X-ray inspection aligns with acceptance criteria for electronic assemblies, and then we'll touch on the conclusions of the webinar. As many of you probably know, X-ray is comprised primarily of an X-ray tube that produces X-ray radiation. that produces a beam that is exposed, or a test object is exposed to the X-ray beam. And given the transmission through that test object, a detector picks up the resulting radiation. So radiation is affected by a number of different things, including difference in materials, whether it be metals, plastics, those type of, composites, those kind of things. Differences in densities as well as differences in thicknesses of materials. And the result of this is a grayscale interpretation. So the more dense a material is, the more thick a material is, the more it will block the X-rays, and that will produce a darker gray image in the result. Also differences in materials. Metallic materials, for example, as compared to plastics or composites, do not block X-rays as much, so you'll get a lighter gray. And you'll see that in the illustrations and the example images that I'll be showing here. To get started with that and to kind of further illustrate how this gray scale interpretation works, here we see a comparison between an optical inspection image and an AXI image. And this is a 3D AXI image. I'll talk a little bit more about the 3D aspects as we go on. As you can see in this example, the PCB material is very visible in optical, of course, because it's picking up reflected light. In the AXI image, the actual PCB board material is pretty low density. So you can see just a weak gray image that corresponds to the PCB material itself. The IC pins are a little bit more dense, and they're also metallic, so we kind of get a middle density interpretation from those. And as you can see, the gray is slightly darker, and you can contrast it against the background of the PCB board material itself. The plastic case is very visible in optical, of course, but not very visible at all. It again is a low density material, so it's not very visible, and you can see components on the other side of the board in this particular case right through it. Then of course we have solder joints, which in this particular image are by far the highest density elements and those that most readily absorb and reflect X-ray so that the X-rays don't get through to the detector. And as you can see from this image, that is very visible. You can very easily see where solder joints are, where the mass of the solder is. Looking in the upper left-hand side, you can easily see a short. That short is visible in the optical spectrum on the left with the AOI, but not nearly as prominent as you can see in the X-ray image to the right. An example of how X-ray fits into a production line these days, as you'll see, I'll discuss this later, but X-ray is being considered increasingly for inline production applications today. Historically, speed has been an issue, but today that's starting to change, so we see X-ray appearing in assembly lines. In this particular case, it's a fairly simple example where we have a loader or some kind of input station. Often this will be fed by a conveyor, for example. And then we have the X-ray system itself in the center. And as you can see from this example, it's the footprint is not terrible. It's a little bit larger than typical AOI system, but not that much more. On the upper right of this image, you'll see our verification station. I'll talk about this in a little bit more detail later in the presentation. And then, of course, we have an unloading or output station, which will either collect units under test or feed into a conveyor system or whatever is set up for the particular production line. Looking at a few requirements that AXI really addresses, one of the requirements that is a challenge these days is inspection of hidden components. As you can see from this AOI image, we have a device underneath the metal shroud in the center right. That shroud is not a heat sink. It's, I believe, just a radiation shroud. So while it has significant density, the density is such that we can penetrate it with X-rays. And as you can see in the X-ray image on the right, we can in fact see the device underneath the shroud. If you look closely at the pin images of that particular device, you can see the varying grayscales for the hill of the solder meniscus. So as you can see here, even through a metal shroud like this, we can often get visibility. This can be different if it's a very large, thick heat sink or some kind of material like that on top of the device. You can't always see through impeding structures, but in many cases you can. For a second example of a requirement, which involves hidden solder joints. In this particular AOI image, as you can see in the center of the image, there are 4 FPGAs. And of course, from an optical standpoint, the connections for those BGAs are not visible at all. Even, of course, from angle view, those aren't visible. But with X-ray imaging, we can in fact see the solder balls on the bottom of these devices. We can see details of the shape and density of the solder balls. In fact, if you look closely at the balls on the bottom devices, you can actually see voids in the solder balls there. So there's a great deal of detail here that we can see relative to these BGA devices. These devices would not be inspectable at all in any other case except for electrically testable. So X-ray gives you direct analysis and access to these solder joints. Another requirement is top and bottom inspection, and looking at the same example here, you can see that we have actually transitioned through the layers of the X-ray image. Again, we're talking about 3D X-ray here, and with 3D X-ray we image the device from multiple different angles, and this gives us the ability to actually separate the Z-axis. So we can see separate components on the top, we can see separate components on the bottom, we can see the solder joints, etc. So we can actually do top and bottom inspection in one pass with X-ray. There are cases where impeding devices or heat sinks or metallic structures, for example, may cause a problem with two-sided inspection. DFT, designed for test, is important in laying out boards to be most effectively inspected by 3D X-ray, so that certainly is a consideration. But as you can see here, when DFT is done properly and board layout is done such that it complements the 3D X-ray capability, very effective double-sided inspection can take place. To talk about cycle times a little bit, as I mentioned earlier, historically X-ray and 3D X-ray in particular has not been widely considered for inline applications because it was simply too slow. Many assembly lines that do use inline X-ray inspection actually will use multiple systems, perhaps 2 systems side by side to be able to accommodate and keep up with the line. But our technology in the 3D X-line systems is fast enough to actually be compatible with typical takt times, and so it is usable in line. To give you an example of why we are fast with X-ray, conventional AXI systems typically use a stop-and-go stepping methodology. Anytime you use a stop-and-go stepping technique like this, you have settling times that are required between images to allow mechanical aspects of the system to settle. Once you move those mechanical aspects and stop them, there's a certain amount of settling time required before you can actually take an image. So the stepping methodology is actually quite slow. We use a methodology where we do a smooth scan. So we don't stop and start for each image, and as a result, the overall scanning of the board takes place much quicker, and it's much smoother and faster, and gives us, or at least is one aspect of what gives us much shorter cycle times. In addition to this, I should mention that mechanically in the X-Line system, we use a staged handling system for the board. So we actually have 3 stages within the machine itself, which allows us to stage boards while one board is being inspected. So board handling aspects of this particular system also help us greatly with speed of test. Typically, we're 3 times faster than a stop-and-go acquisition methodology, but of course that depends on the particular application. One other reason why we are so fast is the Opticon X-Line 3D system is really not intended for as an optical inspection system. It's not intended for visual, high-resolution visual X-ray analysis, such as a CAT scan system or that sort of thing. We optimize speed and resolution. So we go to the resolution necessary to create detection, necessary to avoid false calls, but we stop there for the sake of speed. So we are always looking for that optimum combination of speed and resolution for the inline production application. To give you a couple of examples on cycle time, and again, this always depends on the particular application, but these are a couple of fairly typical real-world situations. In one case, we have a PCB with it is a 290 by 140 millimeters. There are 1,340 components. The design does include multiple BGAs and has a total of over 5,000 solder joints. So complete inspection, 100% inspection of this particular board takes 33 seconds in the Opticon X-Line 3D system. Another example of a slightly larger, slightly less dense board is this case, where we have a 400 millimeter by 230 millimeter double-sided assembly. There are over 3,000 components, which include 22 BGAs and more than 11,000 solder joints. So this board, while it appears less dense, actually there are a lot of solder joints and a high population of BGAs, difficult to inspect targets. As you can see from an optical standpoint, this board would be quite challenging to inspect. But with X-Line 3D, we can provide 100% inspection of this board in 38 seconds. To give you a little bit of a feel for some of our software elements in the system, again, we're talking about an X-ray system sitting in a production line. And in a production line, there will be an operator, of course, that will be assessing failures as they come off of the system. So we provide a lot of software-wise capabilities that help operators of the system quickly determine and characterize failures and determine whether failures are legitimate or false calls, and help them to make that judgment quickly and accurately. In this particular case, I'm illustrating something we call the 3D topo view. On the far left, you see the actual X-ray image of a particular component. The most interesting really to look at is the resistor on the bottom, where you can see the meniscus on each end of the device. If you move to the center, you can see a topographical profile of that solder joint. And again, here you can very clearly see the characteristics of the meniscus on the toe of the contacts. And then moving further over, we see a color-coded interpretation of that particular 3D model, where you can see emphasis of the Z height aspect. So you can see very clearly here how this particular view would greatly help an operator to understand what they're looking at in terms of a failure coming off the system. A few other examples, just to give you a sense of this particular software technology. In the upper left, you see lifted leads in the bottom left of that particular device. And as you can see in the topo view, those are very clearly illustrated. The well-soldered pins on the top, you can see the meniscus on the toe of the contact rises in the z-axis very clearly. But in the bottom left, the solder is completely missing. Similar things you can see in voiding of BGA balls. You can see completely unsoldered gold-wing pins in the center left image. And then in the center right image, you can see voids in a solder under a heat sink. So this is an image of a heat sink that's been soldered down, and you can see clearly the density and composition of voids in the solder layer in between the heat sink and the device. And then, of course, as we saw earlier in an example at the beginning of the presentation, shorts and are very clear. You can see that very clearly in X-ray image on the left, and then even more clearly in the topo view. In this particular example, in the bottom left, we can also see a defective solder joint very clearly. So again, while these failures are very visible in X-ray image itself, they're even clearer, more clear, and easily detectable in the topo view. Let's talk now a little bit about acceptance criteria of electronic assemblies and how that applies to X-ray in particular. There are a number of specs, as I'm sure you know, that illustrate acceptance criteria for electronic assemblies, and X-ray certainly helps us to gain compliance with those requirements. A good example here is a gold-wing, a typical gold-wing pin. In this illustration, you can see the gold-wing pin with the solder joint, a corresponding solder joint. A secondary criteria for inspection here is actually the forward meniscus of the solder joint. That is visible, of course, in AOI in a number of ways. It's also visible in AXI. But much more challenging in most cases is the primary criteria, which is often only visible to AXI. Under certain circumstances, we can visualize that solder aspect with an angle view, an AOI angle view, but it's much more effective in AXI. You can see the profile of the hill much more clearly, the density of the solder, etc. So again, I'm going to talk a little bit more about AOI later on. So we should illustrate here again, this is a really powerful combination of the two, where we can produce 100% and very effective inspection. A few other examples that correlate with acceptance criteria for electronic assemblies are represented in these two AOI images. The top images is a orthogonal top view of some soldered pins. The bottom image is an AOI angle view, which is angled at a 45-degree angle. And as you can see, as I mentioned earlier, you can see in the pins on the right in the lower image the heel of the solder meniscus from this angle view for the pins toward the end. But of course, as we get into the pins in the interior of that row, that visibility becomes much less prominent, and so visualization of the heel of the solder joint in that particular case is problematic. However, if we look at these examples in the X-ray image, as you can see on the right, we can very clearly see the heel of the solder joints, and they're very dark and dense in color. So we know that that is a very good and strong solder joint. If you look at that in topo view, of course, you would also see a very strong representation of the healthy profile of those particular solder joints. However, if you look at the bottom, you can very easily see some very, very bad solder joints, and those are really not solder joints at all. They are largely unsoldered pins. If you reflect back on the visual image You can see there the undersoldered pins are not nearly as prominent and obvious as they are in the X-ray image itself. So again, this is an example of the contrast between AOI and AXI. With AOI, we can see most obvious prominent failures, but there are a lot of failures, failure potentials there that are much better imaged and revealed by X-ray. Another example with a set of pins here that have another failure characteristic. Again, in AOI, you could see these pins, and I can tell you that our AOI system would certainly be able to detect failures in these particular pins. As you can see from the reflections, there are problematic solder joints here. But it's not always completely obvious what the nature of the problem is from the optical standpoint. However, if we look at this in X-ray, we can much more clearly see the characteristics of the solder joint. In the bottom left and right rows of pins, you can see very healthy solder joints. And then, of course, in the top, very poor solder joints. And again, if you compare that to the optical image, we could certainly detect those pins, those faults in our AOI system, but it's much more effective with the X-ray backing it up. Not to overburden the issue, but it's always good to look at examples, and here's a few others. Here are some gold-wing pins that again are unsoldered. They're actually lifted and offset a bit, as you can see. And looking at this in topo view, again, you can very clearly see the problem. If you look at the pins on the upper side of the topo view image, you can see that the heel of the solder meniscus rises very prominently into the z-axis. However, in the pins in the lower right, there's really no solder meniscus whatsoever, and you can tell very clearly that this is a bad solder joint. So again, in the optical image, we can see a failure. We could probably catch this failure with AOI, but to characterize the failure in more detail, X-ray brings a lot of additional information. To take a little bit more of a look at our verification station that I mentioned earlier, just to give you a little bit of a sense of the software that is used on these systems. This, of course, is only just a very brief glimpse of the software, but it will give you an idea. On the left image here, you can see a schematic view and the original X-ray image. This schematic view, this is kind of poorly composed. There's actually a crosshair just under the corner of that window that's forward that actually shows where in the particular schematic view the failure resides. So that particular view shows you exactly where on the board the failure is. The window to the right shows you a close-up X-ray image of the device and the failure. And then, of course, the top image on the right very dramatically illustrates the issue with the upper right pin. So this is an example of the software, for example, the operator of the system would be looking at. So when there's a failure exhibited on a board, they would get this view, and as you can see here, they can very quickly and easily identify in great detail the nature of the failure. So this adds a lot of capability to the operator's ability to more accurately identify failures or false failures. Here again is another example. This is an example that's actually quite dramatic and surprising in a number of ways. When you look at the optical images on the left, it's not real obvious that there's a problem here. Very careful programming in AOI would likely catch this in most cases, but I know for a fact that we've seen many escapes of solder issues like this. And if you look on the right, the X-ray image and the topo view images, a problem becomes much more prominent. In the left X-ray image, For the SOT23, you can see very healthy heel on the solder meniscus. And the right, of course, you see a very poor solder joint, and then that is further illustrated in the top of view itself. This is actually a case of an inverted device. So this device is actually glued down to the board, but it's been inverted during assembly, so there's no solder joint whatsoever there. From the optical standpoint, that's not all that obvious. It would be made more obvious from an angle view with AOI, but again, X-ray brings even more information to the table. To illustrate a little more relative to QF pins, QFN pins, as you know, these pins can be somewhat challenging to inspect because the pin contacts are largely hidden. As you can see in this X-ray image, the forward meniscus is very clear in this image. And again, with topo view, you can see a very dramatic characterization of the solder joint itself and the meniscus as it forms on the leading edge, the toe of the contact. So again, here you can see very prominently, even on a challenging device like a QFN, the exact nature of the solder joint. In this particular image, you also see some voids in the solder layer that forms a bond with a heat sink on this particular device. And we can look at that a little bit more closely. Since this is 3D X-ray again, we can separate the Z layers of the image and be able to isolate the solder layer that bonds the heatsink to the device and very clearly illustrate the voids that are involved here. In these particular applications, I don't have a really good example of it in this presentation, but we can actually calculate percentage of the void, the percentage of the area that's involved in voids, the distribution of voids. There's a number of statistical elements of analysis of voids that we can bring to bear with the software. Again, taking a little bit closer look at the verification station here. On the left is the visualization station that shows us the schematic view and shows us the location of a particular failure. On the right image, we see the X-ray image itself. In this particular case, it is a package also that is soldered down to a heat sink. So you can see voids with a heat sink, and you can also see the pins, the solder joints on the pins. And that is visualized very clearly in the topo view image on the right. And then there is a classification keyboard, a specialized keyboard that helps the operator or programmer classify failures as they come off. One more example that illustrates a different type of heatsink application in the form of a DPAC package. Here you can see a little bit more clearly how the schematic view has crosshairs that shows you the location of the failure. And then again in the bottom right view, you see the X-ray image of the device and the topo view of the device that illustrates not only the solder joints, but also the nature, the homogeneous nature of the heatsink solder layer. To move on to a slightly different subject, THT, that's through-hole solder joints. These also can be quite challenging in AOI applications. In this particular image, you can see in the bottom center, there is actually a pin that is not soldered. In the center part of the image, you can see a solder joint where the pin is not protruding from the solder joint itself, so it's not really totally clear if the device is actually mounted there. And then on the left there, you just see an unassembled hole. Looking at this a little bit more closely, a through-hole solder joint does not only consist of solder contacts on the surface, it also consists of the barrel fill or the solder fill of the hole itself. That is something that is not inspectable really at all with AOI. Electrical tests can reveal problems there, but often does not. Barrel fill issues are probably more of a lifetime or dependability problem, and not usually detectable immediately through electrical tests. So this is an application where X-ray can become very important for inspecting high dependability through-hole joints. And again, we can characterize some of the failures through through-hole assembly with AOI. If we look at a case like this particular connector, we can take a look at the pins themselves. Are the pins deflected? Are they out of place? Are they in place? And we can see that with AOI. We can look at the bottom side of the board, and we can look at the solder joint as it exists on the surface and look at the nature of that particular solder joint. However, with 2D X-ray, we can actually see the density of the solder joint more clearly. And with 3D X-ray, we can actually see through the entire barrel fill element of the hole. So we can characterize with 3D AXI the actual fill of the hole itself in terms of the percentage. To look at this a little bit more closely, let's look at this particular illustration. As you can see here, we've got an illustration, a 3D illustration of the solder in the through holes. If we take a look carefully, we can actually profile these particular solder joints at different levels in the Z aspect for the solder joint. And as you can see here, while this solder joint may look just fine on the surface, as we descend down through the hole, we can see issues. And if you look at the solder, the X-ray image on the left, in the third and sixth rows, you can very clearly see examples where the hole is not properly filled with solder. So those are potential dependability issues down the line. And in many applications for high dependability electronic assemblies, this can be a very critical consideration. So this is an application where X-ray is very clearly needed and very clearly useful. It illustrates something that is really not detectable in any other practical way. Just to look at a few other assemblies, fault types. Here are some resistor images that illustrate a various range of failure problems, solder joint problems. In the top, you can see, for example, there's no solder at all there. There's really just paste. In the images proceeding to the right, you can see just very poor soldering. You can see what looks like probably a cold solder joint, and then a more proper solder joint on the right. In the lower images, you can see various types of offsets, various types of lifts of this particular resistor component. And those make for a few good additional examples of the imaging in X-ray. If we look at these resistor examples, as you can see from this optical image, we actually have a resistor in a tombstone situation where one end is completely lifted. As you can see in the X-ray image here, that's very clear. You can see a very unusual meniscus profile on the right, contact to that resistor, and then of course the complete lack of a solder joint on the left. And then of course in the topo view image, that becomes even more prominent. In the upper two components, you can see a very clear and normal meniscus on the contacts. However, in the lower image, you can see not only that the contact, the solder joint on the left is completely missing, but you can actually see the dual meniscus on the resistor contact that gives you some idea of what's going on there. Whoops, excuse me, I just hit the wrong button. Sorry about that. Just do a quick reset here. One moment, we'll get back there. Just consider this a quick review. Okay, here we go. Sorry about that again. Anyway, back to where we were. Here's another case with a resistor that is actually billboarded. So this particular resistor is offset laterally. It's actually sitting on its side. So there is in fact a solder joint on each end, but as you can see in the optical image as well as the X-ray image, the solder joint is very unusual. In the optical image you can clearly see something's wrong. In the X-ray image you can see additional information there that illustrates what's going on. And then of course in the top of the image you can also see very clearly that there's a problem. So again, this makes this very, very easily identifiable in terms of the failure, the nature of the failure. Another look from the standpoint of the verification system, verification station. As you can see here, the schematic aspect is very clearly illustrated in terms of where the location is. Oops, sorry about that. Someone just pointed out to me here. I need to go back to full slide view. There we go. Thanks, Patrick. Anyway, back in the schematic view, we see here very clearly the location of this particular failure. In the X-ray image, we can see that there's definitely a problematic solder joint on the right contact of this resistor. And again, in top of view, that's very clearly illustrated with the very healthy meniscus on the left contact, but a very poor solder joint on the right. To touch on a little bit different subject here, capacitors are a little bit different creature in X-ray. They are very dense and of a material that does not allow transmission of X-rays very effectively. So unlike the resistor example where you can very clearly see the metallic contacts on the end of the resistor and the body of the resistor itself is largely invisible, in the case of a surface mount capacitor like this, the entire capacitor illustrates its density, so it's a little bit more of a challenge for inspection. The software helps us deal with that. When setting up a program, the software allows us to profile what a capacitor should look like. And again, I should point out here that this is all library driven. One of the aspects of the software setup and programming in the Xline 3D system is that the software is driven very effectively by a very robust library of components. And these components, the nature of these components are defined, of course, and with respect to capacitors, the nature of the device, the package, and the solder joint is defined, which helps us to produce proper detection for these kinds of components. Again, from the verification station point of view, we can easily see the particular component being observed. We can see the X-ray image of the component in the lower right, and then again a topo view of that particular component. To talk about BGA solder joints in a little bit more detail, this is naturally a very active subject in X-ray inspection. BGAs pose many challenges. They pose challenges to electrical test due to lack of accessibility. Goepel actually deploys and develops a very robust line of JTAG boundary scan related products to help with electrical tests and these kind of challenges. But for optical inspection, X-ray is really the answer for BGAs. There's very little that you can do from an optical standpoint for a BGA, but with X-ray you can reveal a very great deal of detail. In this particular case, you can see a imaged BGA, and its particular balls, where we can see the shape of the balls, we can see the density of the balls, we can see the shape of the balls gives us a lot of information that relates to the quality of the contact. In this particular example, we can see numerous voids within the solder balls, so there are a lot of detailed characteristics here that are revealed in 3D AXI. Solder ball issues come in a number of different forms. Here's a case where there's really no solder contact at all. You can see the ball sitting on paste. Other cases where there's just a very poor solder joint, partially soldered. In this image you can see that there's some solder flow there, but there's also, it's really just kind of sitting on paste. It's not completely soldered. And then of course the head and pillow case, which many of you have probably encountered or at least heard of. And then of course a nice healthy solder joint. So if we look at some of these aspects in the X-ray domain, we won't go into a lot of detail here because frankly there is a lot of detail and complexity involved in BGA inspection. But just to give you a sense of how this all works, we detect the ball basically through its shape. We measure a number of different values: the area of the ball, the compactness, the axis ratio of the ball, the mean grain gray value of the ball, as well as the mean gray value of the background. So this gives us the ability to characterize a solder ball in situ. Detection of voids is very clear in 3D X-ray like this. As you can see here, the density is very easily revealed. We can measure void area. We can measure the percentage of void area relative to the ball area, and as a result provide very valuable metrics in terms of being able to guarantee certain criteria relative to voiding of solder balls. In this case, we see a well-soldered BGA ball. In other cases to the right here, we see examples of head and pillow. And as you can see here, the characteristic shape of the ball is very unusual in the case of head and pillow. Head and pillow comes in a number of different forms, but it's generally a resist-oriented reaction, which results in the deforming of the solder ball. And with 3D AXI capabilities, we can actually measure the ball at several different areas in the z-axis to characterize the shape and normality of the shape of the ball. Again, we can measure axis ratio, the compactness, the area, and then probably most importantly in the case of head and pillow, the actual shape or deformity of the ball. So again, this is a issue that's very prominent in today's circuit board assembly, and one that's probably amongst, if not the most challenging issue out there being dealt with. And X-ray comes very close to providing very effective detection for these. It's not always detectable. There are many variations, as I mentioned, in head and pillow cases, but in many cases we can in fact detect head and pillow faults in solder joints, and as a result we can definitely greatly improve the effectiveness of inspection of BGAs from that particular aspect. Again, I want to come back to the combination of AOI and AXI. We've been talking primarily about AXI, but there are very good reasons to merge AXI with AOI. For example, fiducials can often be difficult to detect in X-ray unless the fiducials are soldered or otherwise treated to make them visible to X-ray. This can be a challenge. So combining AOI with X-ray can be very effective in helping with this kind of setup issue. OCR, OCV, data metrics codes, just reading codes on a device, of course, is not possible with X-ray. So again, combining AOI capabilities within an X-ray system is very powerful and rounds out the capabilities of the overall system. In addition, polarity marks are not usually detectable with X-ray, so AOI helps there. And colors or color coding is not detectable with X-ray. So having a very accurate colored AOI capability rounds out the overall solution in that area as well. To talk a little bit about our particular AOI systems, here you can see a combination of AOI and AXI, where with the AOI system we can easily see polarity marks, we can easily see markings on devices, we can see color coding, colors involved in the assembly, etc. And then in the X-ray image we can see both sides of the board very clearly, as well as BGAs, etc. And to go into a little bit more detail on our AOI capabilities, our illumination systems are very powerful, and one of the keys to effective detection and avoidance of false calls in AOI inspection, we have a number of different aspects. Going into detail on our AOI system capabilities is really a webinar in itself, but I did want to at least touch on some of the capabilities here, since the message I really want to deliver in this webinar involves the combination of AOI and AXI. We have top flash illumination that helps with polarity check, presence, OCR, printing, barcode reading, color recognition and verification, as well as image acquisition of color overview images. As you can see here, the color capability is very clear. The ability to see markings is very clear and optical. There are challenging areas where contrast becomes very important in optical inspection. We have some capabilities such as an infrared metaflash illumination. Our illumination capabilities really are full spectrum from infrared to UV. So we can produce an infrared capability that helps in many different cases of challenges with contrast. In this particular optical image on the left, as you can see, those SOT packages are almost invisible. However, when you look at them in the infrared spectrum, they become very visible. The markings are visible, the bodies are visible. The overall contrast is greatly improved, and the understanding of the makeup of the board is greatly enhanced. So to round up, we're running a little bit short of time here, so to kind of quickly round up conclusions, usage of X-ray technology is very important in conforming to IPC inspection requirements. Test of hidden solder joints is possible. Real test of real solder meniscus profiles is possible. The real test of tin hole fill in THT applications is possible. Independent of reflections and shadows, or I should say X-ray is independent of reflections and shadows, which often AOI depends on very highly. We can provide safe detection of critical solder joints, such as lifted leads with X-ray. Technologies that are necessary is a 3D X-ray system to separate top side from bottom side. 3D is very important in X-ray inspection, particularly from a performance and cycle time aspect. Short cycle times are needed to keep up with line speeds, and inline X-ray is an investment for the future, and especially in applications where testing of high dependability PCB assemblies is involved. So thank you very much for your attention. I hope you found the presentation interesting. And as I mentioned earlier, we're always happy to follow up. I generally follow up. And but feel free to contact us if you have questions or would like more information. And with that, I'll throw it back to Phil for questions.
Okay. Well, thanks very much, David. Very interesting presentation. Some great images there that really give us a good idea of what's going on. I've unmuted Patrick. I can hear his microphone's working because I can hear some background noise at his desk. Patrick, can you just quickly introduce yourself so everybody on the call knows who you are?
Yes, my name is Patrick Schuchert. I'm application engineer for X-ray and AOI here for the Goepel US office, and I'm open for any questions if you have
Okay.
something.
Perfect. Okay. Well, I've got a couple of questions come in, but if anybody else has them, just go ahead and type them in now. I'm conscious that we're only a few minutes away from the end of our hour, so we'll get straight on with those. First question, and I'm happy for Patrick or David to chime in on these. Can the X-ray detect head-on pillow defects? If so, what is the false call rate?
I think maybe that question was before David
Okay.
had the slides because he was talking about head and pillow. Head and pillow is indeed a critical test, and we believe we can test the majority of head and pillows, but there are cases where it is not 100% safe. Especially this one slide David had, where you just really have a perfectly shaped solder of of the BGA ball, and it always depends on how that head and pillow is shaped, because you see here in that slide, we go after the shape. We cannot slice it thin to see the actual edge or border between good and bad. So here we see if the shape is bad in the center, we can say, okay, that's for sure a head and pillow. But David, if you go back one slide where we see the actual head and pillow images, I'm not sure where it was. Yeah, right there. So the third picture, it is a head and pillow, but the shape is almost good. And what we go after here is the diameters of certain slices, and this one is still detectable, but it becomes clear that it is hard sometimes to detect. So to answer the question, yes, but there might be cases where we will be not able to be 100% sure.
Yeah, and you get the odd false detect as a result of that. Okay,
Yeah, I
I'm
think
curious.
particularly with head and pillow, it's important to consider that bringing as much detection to the table as possible is where the value is.
Yeah.
You may not be able to always detect, but we can greatly enhance the capability to detect.
Yeah. One of the things I was curious about, David, is when are you advocating using AXI and AOI all the time, or are there instances where one's more successful than the other? And how do you choose whether to do one, whether to do the other, or whether to do both? What's the kind of strategy there? Is it dependent on the assembly mix?
Yeah, certainly it does depend on the assembly mix. It also depends on the test requirements and the nature of the board and the application. Patrick, you could probably characterize that from real-world examples.
Yes, I always say a healthy mix of all test methodologies available in your line is the best way to go. You need to have electrical test, you need to have AOI, and if you have hidden solder joints like BGAs, you need to have X-ray. That's the quick answer. Again, a mix of all your test methodologies is the best.
Yeah.
Okay. You may run into boards that are very simple and don't have challenges, and AOI may be perfectly capable and faster, frankly. So there are possibilities where the mix would change, but as Patrick mentions, I think bringing all capabilities to bear gives you the greatest possible test capability.
Yeah, and that really leads me on to another question. As well as it giving you the best fault detection, surely it would give you the best feedback to correct the process. And that's a big part of it, isn't it? Providing that feedback loop so you can not just see that you've got a fault, but you can see what that fault is and perhaps where in the line that fault's coming from.
That's a huge point, and that's one of the reasons we emphasize so much the topo view images, and almost we're overbearing on those in the presentation, because that is such a powerful tool in terms of being able to characterize clearly the nature of the issue, especially when you're dealing with an operator that's having to classify failures. Those that you get so much information and so much clarity out of the system that it greatly enhances that. Patrick, anything to add there?
Yes, and Philip, you are absolutely right. It is about an indicator of your production process. So what you test here is not only failures and passes. It's also tells you how is your oven profile. If you have a solder joint like in the first image here, then something is wrong with your temperature or your soldering mass.